But yeah. Hungerford has a book that's undergraduate algebra. So like first chapter is like adding your mod to n. I mean, it's just like, come on. You guys can be smart. Although I do like that Hungerford starts with rings. I think that actually is good. Rather than groups. Second here. All right. Hey. Massive. Tim, you really don't have to sit all the way in the back.
I know. It's just that I'm so used to it. It's just like.
Please feel free, but it's okay. If you're more comfortable, that's fine.
No, trust me. Usually when I'm in class, I'm not
Yeah, I used to do that too. So guys, what do we have? I am blissfully ignorant of what I've assigned.
It's only 4 problems.
Only 4 problems. So what can you tell me what they are?
They're 4, 1, 1.
4,
413. 413.
413,
Oh, it's 5. It's 5, 1.
511.
5, 1, 3. I think it's 6, 1, 3.
6,
6,
Yeah, see, guys, it's not much. Not much.
Yeah.
It's a lighter assignment. I think when I was making this, I remember the last homework problem set was pretty long. I got a lot of, you guys did a lot of work. And it was good. I mean, there's a lot of good answers there. So this one, I'll take it easy. Ebb and flow. All right. So have you looked at any of them? Any of them look?
The one that scares me most is
513 is terrifying. Let's take a look. 513. All right.
I just don't know where to start. I think that's my issue.
Ah. Yeah, good question. Nobody knows the answer. All right. Well, what do you think?
It was confusing at first. I thought that was a 1.
Yeah. Oh. Yeah. I think they mean a 1. Well, it's okay. I don't know. It doesn't really matter. Whatever you want it to be. What you don't want is you don't want to consider this to be an element of ON, I guess is what I want to say. Like, in other words, you shouldn't think of this guy as being in here. Because of course, if like n were 2, right, the negative identity has determined a 1.
Right, right.
So, so you don't, so you don't want to think of this as like an n by n matrix. You could think of it as an odd n by n. I mean, you could think of it as an n by n matrix too. You just don't want to think of it as being an ON. It's like a separate group. This is a separate group. Just plus or minus. I mean, it's just isomorphic Z mod 2. That makes sense? No. No?
Wouldn't it be a part of ON anyway, since this determinant is always gonna be one?
It's not going to be. It's going to be -1 when n is odd. It's going to be 1 when n is
Yeah,
even.
that'd still be a part of ON.
It will be a part of ON, but I'm just saying you don't want to say, okay, if you take it as a group on its own, then this question stands on its own. If you take these as two subgroups inside of ON, then this is not going to, it's not going to be correct. Because so there is a theorem. There is a theorem. Way back in the day, probably last week, where we proved something about showing whether or not a group is isomorphic to a product, given two subgroups of that group. That's what I'm referring to here. So let's see if we can find it. I'll go look in the book. I have no idea, no recollection of the number, but I'm assuming it's in the section on product group. They're going to probably maybe 2 weeks ago. So this is a proposition that is meant, well, it's helpful, probably pretty helpful in answering this question, so long as you take into account what I just said. Okay. So maybe the first thing to do is let's assume n is odd, and then we don't have this trouble. If n is even, there's something else we can do. But then you have to just have to interpret this in the right way. I assume that so I'm assuming Artin means this in the right sense, which is these two groups, I'm going to say it again, these two groups stand by themselves. They're two separate groups. Two separate groups. Is that clear? They're not satisfying this hypothesis. Now that I've said that, let me assume that n is odd, in which case they satisfy this hypothesis. So for n equaling odd, we're fine. It's okay. Because, well, they still satisfy it for n equaling even, but then we're not going to get anywhere because we're not going to get A. A is saying that they should intersect in only the identity. And if n is even, negative identity is in SON. So I don't have A. So I don't want to consider that case. I'll deal with n even in a second. Okay. Sorry. I probably should have first said, hey, remember that, rather than say starting off with that, but it's just what came to my mind immediately. So let's assume n is odd. Now, let's see if everything works here. So A is true. So here I'm and let plus or minus 1. I guess. So I don't know, we can call this, okay, so I have to it's K, SOMH. That's G. So now that I made that connection, let's check. So A is true. In the sense that still ahead of myself. Let me try one more time. So take F to map from H is this one, SON. So N given by the product. All right. Now, what do you think? A is true. F is inject.
Show that they're normal subgroups.
Well, do we? I thought we just need to show that H is a normal subgroup and that these things, H commutes with everything in K. This right now is a map. This is just a map. So is H normal? Is SON normal?
Definition.
I don't know. I know, but I don't know. Like you tell me, why is it normal? It is normal. Why is it? Yes. Why is it normal? In this is normal in ON, not in GO. Yeah. So definition of normal means I can conjugate it, right? So what is this? If I look at any matrix B, I make this conjugate and A is in SON, then I can take the determinant of this. Is equal to determinant of B, determinant of A, determinant of B inverse. This is 1. That's 1.
Because B is in ON.
Well, B is in ON. B being in ON tells us that this is orthogonal. If B is not in ON, then that may not be an orthogonal matrix. So, in which case we would be outside of both SON and ON. So, but if we're in ON, then we're staying in ON. And furthermore, the determinant is going to be, so it's an SON. This guy's an SON. Yeah. So yes, it's normal. Which means that HK, which means the image of F is a subgroup. And now what about B? Sorry, this is C. What about B? Is it the case that this is a homomorphism? You guys tell me.
Yeah, I mean, definitely that's a one question, but I'm trying to figure out how that applies here.
Okay. Yeah, don't, I mean, look at the definition, look at what B says. It's a homomorphism if and only if when I take an element from K and an element from H, they commute. Is it true? In this case,
Yeah, because the energy is invertible.
not just invertible, it's the identity. So invertibility won't help me there, but just that that I is identity, but negative I also will commute. In fact, you had this exercise where you said, look, what is the center of GLN? Right? What is the center of GLN? And the center of GLN you found you should have found that this is a constant times the diagonal times the identity. So -1, our negative identity is constant times the identity, -1 times the identity. So this -1 commutes with everything, 1 commutes with everything. So B, conditions for B, HK equaling KH, this is satisfied here. So F is homomorphic, is a homomorphism. Now, all we need to do is it's an injective homomorphism. If it's surjective, life is good, we're done. So is it surjective? So we just need to show HK equals G. Is it true?
Because the determinant of H is equal to 1.
Determinant of A. You mean if there's an element of H?
Yeah. The determinant of element of K is equal to 1.
I mean, be a little more. I think you've got the right idea, but maybe help me out a little more.
So is it kind of like what's the determinant of an element in G is 1 or -1, and it's the same SON, or if the product results from H and K, then there should be a method between every H, K, and G.
I didn't hear you say determinant. Did you say determinant?
I did, but I think I only said.
So I need an argument here that's really about determinant. So let's just start with an orthogonal matrix. So suppose A is just any orthogonal matrix. We want to show that we want to claim that it's in this product. Let's do a couple of cases. If determinant of A was 1, well then is an SON. And so A equals, which is H is SON. A times 1 identity. If, on the other hand, determinant of A is negative one, these are only two possibilities, then what can we do? I want to show it's in SON times.
Doesn't belong to SON.
Belongs to O.
Oh, and then minus.
Well, what else has determinant -1 in this case? Remember, we're just in the n equal 9.
Let me just kind of use that out. Did it be inverse that determinant negative one?
Of what? Of A? Yes, A inverse will also have determinant -1, but I don't know how I can leverage that. I want to, so what else have we just been dealing with that does have determinant -1 on the board here? Negative identity. So then determinant of A times negative identity, what is that? One. Product of determinants. So this is where? This is in SON. Applying. Well, say this is equal to B. Applying A is equal to B times -1, just multiplying both sides by which is in the product. So we're done. So it's an isomorphism. When n is odd, yes. So in the interest of fairness, what do you think is going to happen with n being even?
The determinant of the energy only has one.
Okay, so listen. I'm okay with that for all you at home and you here. If you want to just say that, that's fine. That is true. So if what Artin means is you consider this as a subgroup of SON or of ON, then yeah, these things are, A is already false. And so we don't have, this map is not going to be an isomorphism. We don't have an injective map. So if you want to say that in the homework, that's fine. That's enough. But I actually don't think that's what Artin means. In which case, this is false. Even then. But these are not isomorphic. And the problem is you can actually, there's something like this that's true. Is what I want to say. Something that is like this that's true. And it's called a cross product. It's not the cross product that you're used to from calculus, but there's a cross product of groups that allows you to sort of generalize the notion of product. And you can realize ON when n is even as sort of a cross product. But let me just explain, in the case of n equaling 2, why this is false. The reason is what do you need for this, if this were true, if O2 is isomorphic to SO2 plus, I'll just write 1 here, plus or minus 1, you would need to find this -1, to find some A and O2. That's very special. What makes this special? Well, it has to satisfy A squared equals the identity. A is not in SO2. It was in SO2 the whole time. And most crucially, A commutes with everything. It's in the center. Center of O2. But what we saw today in lecture with O2 is we saw that we can write down precisely what the matrices of O2 are. They're one of two types. They're either a rotation or a reflection and a rotation. In fact, the ones, if you look in Artin, he's more says something a little more that I didn't really want to spend time doing, but the ones that aren't rotations are in fact just reflections, period. In other words, you can find some line through the origin that these are reflections. So A has to be such a reflection, but those are not going to commute with all rotations. If you rotate and then reflect and then rotate inverse, you do not get the same axis of reflection for any rotation. So that tells you that you don't get an isomorphism. There's no such A. However, there is still this map from O2 to, plus or minus 1 to this group, and the kernel of the map is SO2. So you still have this sort of isomorphism between the quotient group. So it's very close to being like a product of groups. You can kind of quotient out by SO2 and get, that's not actually not subtle point actually. Okay. Is that it? Everyone happy?
Oh, for my other question?
So, could we,
How would you prove this for ON and general N? So,
or, yeah, but also for this, do we even need to do the first part, or since it's not isomorphic for all values of n?
well, I'd like to see that. I'd like to see, because, we did spend some time, talking about this proposition. It's a good thing to, when I did spend a little time on like kind of trying to structure this course, like, so that the things that we covered would be used. So it'd be good if we can remember some of those things. You don't have to you don't have to write so much. I know you type yours, and so which I appreciate, but you just can, summarize the argument if you want. It's up to you. Oh, I love it. You guys see my handwriting is awful, but yeah, I don't do it. Don't do me any favors,
Okay.
unless you want to.
Let me know if my handwriting.
No. Actually, okay. So let me make one comment. Some of you guys are all great. You're all wonderful people. I'm never going to criticize you. But if you're uploading your homework, it would really be great if you could upload it so that I can read it. So that it appears when it's uploaded like this way instead of this way, so that I don't have to go to my settings and turn off auto rotation. Because I can't on Canvas Grader, it's not your fault, it's Canvas Grader. I can't find how you can rotate images. So I literally have to read some homeworks like this or turn off the rotate. So
upload images horizontally.
upload them so that most of you are doing it right. So, but some of you are actually uploading the images so that when you look on the images in Canvas, if they're turned like 90 degrees, I'd rather they not be turned 90 degrees. Most of you are doing it fine. And I'm not like, I don't take it out on people that aren't doing, I mean, I still try to create just the content. Anyway, just a comment. It's okay. Anything else?
Maybe we could do one of the example.
5.11.
Or yeah, 5 on the rotation.
Yeah, I don't remember. One. Okay, this one. Determine the matrices that represent the following rotations of R3. Okay. Angle theta, oh, these aren't. Okay. Angle theta, the axis E2. Yeah. Well, okay. Arden's, look, he's using the standard basis. So yeah, you're right, the y-axis. Axis C2 is the y-axis. Angle 2 pi over 3 axis containing the vector 1, 1, 1. That's a good one.
The one where it's just.
Smart guy. Smart, yeah, that's the one. Very smart. Angle pi over 2 axis vector blank. Which one do you want me to do? Which one do you want us all to do? Isn't that the one? Me too.
I would say pi over C is the hardest one.
C is the hardest?
I don't know.
I don't know. I think it's the hardest. I don't know. Think about it. Okay, I got it. Directly about it. Probably not. All right. Yes, I think you're right. I think C is the hardest. So let me copy this.
I just out of those 3.
The first two, I can give you an answer right away. The third one, you're right. I have to think. So let me just, I want to draw a picture because I want to see if I can do it. If I don't get anywhere, then I can do something more algebraic. So the vector, I mean, if I use my usual coordinates here, I mean, I have some axis of rotation that's sort of this way. This is in the XY plane. And the angle of rotation is pi over 2, so I want a 90-degree angle, which means I'm going to send my XY plane to the plane that's sort of like, it's made up of this guy. That. So now, so here's how you can, okay, so here's how you want to do this, right? Or how I want to do this. And how you would generally do this, right? You want, how do you find the matrix of a linear transformation, period? Okay, that's key. So more important than this problem is how you do this generally. So I've got a transformation. I'm going from Rn to Rn. I'm gonna write down a matrix that gives me this as multiplying by a matrix. What I need to do is I just need to check, I want to look at where the ith basis vector goes. It goes to some vector vi. If I know where what these vectors are, then I can write down that matrix by just taking the matrix to be v1 to vn. Put these in the columns. Okay. So now that I know my geometry, I can try to do this in this case. So what are these EIs? So they're in calculus, call them I, J, and K, right? So we have these three guys, just our unit vectors on these positive coordinate axes. I want to know where they go. Maybe I should color it. This red. Okay, well, green is good. Green I can do. Everyone can tell me where green goes. So green to E3 goes to what?
We're talking about A or C?
C.
We're talking about C. Oh,
Yeah, don't know what green goes. But he knows. Huh? Maybe I don't know what green goes. Okay, hold on a second, guys. I need to help. I need to give my axes negative. Now, okay. Where's green? So, okay, green is going to go. Can you tell me where kind of qualitatively green goes? Yeah, it's going to go to the XY plane, is what I want to say, right? We're rotating now. I don't know which way are we rotating. I was thinking we'd rotate like using a right-hand rule, I guess. I mean, we can either rotate right-hand rule 90 degrees or left-hand rule 90 degrees. But I think probably right-hand rule is the convention.
yeah.
Okay. So, right. Okay. So, well, counterclockwise about the direction.
Yeah.
Yeah. Okay. So I think what happens is we're going to go like that. Right. All right. So what we're going to look at then is where is the line Z going? Do I have a green? Yeah, I do. The line Z goes to this line.
-1 or 1 -1.
Well, hold up. Hold on. So it's easy, but it's not as easy as I. Right. So Kale just gave us a point on that line. But that point, right, which would be 1, -1, which is close. So it suffers a defect. So the candidate right now is 1 - 1, 0. What's wrong with this point? The length. This is an orthogonal transformation. The length of this is square root of 2. So what do I need to do? Normalize it, right? So let's just divide. Okay, so close, but I just need to multiply square root of 2 over 2. Great. So that was fun. Now, what we did here, we can probably do for blue and red friends. So now we have to go. Okay, so now what we know is we're going to be going. Okay, so blue is going to go into this plane. It's going to go like this. Okay, so let's.
√3 over 3.
Right, it's going to go here. It's making a 45-degree angle here with this axis. And yeah, so we want to say well, okay, so what, Kale has another candidate that E1 is going to 1, 1, -1. Which so, and I think the reason he has that is because he knows 1, 1 is here. And he dropped it down and he knows that that makes this angle 45 degrees. Does it make the angle 45 degrees? No, it does. Kind of. It's just all of a sudden. Hold on. I'm suspicious. Did I be suspicious? I think it's a little bit off. I think what I want is rather not 1, 1. You have to normalize this, right?
Oh, yeah.
You have to normalize these guys. Square root of 2 over 2, square root of 2 over 2. And then if I go down 1, now this vector will make a 45-degree angle. But this is like this kind of a thing. But in that plane. But now this is not normalized. And so I have to renormalize this, which is not so bad because this is going to be just dividing by square root of 2 again. So what I'll get, so normalize. Well, the point is I want to make this triangle, right? I know that what's going to happen is I'm going to take the XY plane and I'm going to rotate it. So that it becomes this plane here. Right?
Yeah.
And this axis of rotation is not going to change. And so this axis of rotation makes a 45-degree angle with this blue, with this blue line, or with E1. So when I rotate it, it'll still make a 45-degree angle. So what I did is I said, okay, well, take a unit vector here, and I'm looking this plane, and what do I have that's a 45-degree angle with this unit vector? And that is just for which I'm taking this and adding some negative of z. Well, if I take -1, then I know I make an equal at I make a equal at not equal isosceles triangle, right triangle with equal side lengths. And so I know I get a 45 degree. So this gives me that line, but I want this to be unit vector, so I know. So now, again, if I square this, I get 1/2 plus 1/2 plus 1, so that's 2. So I have to divide by square root of 2 again. And that should give me 1/2, 1/2, negative square root of 2. But now we've done all the hard work for E1, and E2 is kind of the same idea, but what do I have to do for E2? So what should I write here? I would never call this. So the picture I just drew, this mini picture I just drew, was like, I wanted to know where this went, so I just drew this triangle. I'm taking that XY plane and rotating it to this point. But I'm taking the XY plane and rotating it to this point. So I'm going to have this kind of a triangle. Yeah, this it's getting a little messy.
So we'll just do 1/2, 1/2.
Just going up now in the Z direction. Right. And so we're done. We can write this down. So the matrix. Okay. I'm not telling you guys this is the best way. I'm telling you it is a way to do it. I'm not writing this down. What's that?
Seems like if you're good at drawing.
Yes, I think that having a little experience with some of the drawing, this should be negative. Drawing things is helpful.
Can we check if it's right by multiplying it by the 1, 1, 0 vector? And we should get the 1, 1, 0 out.
For the 1, 1, 0
With
vector.
the one with the axis we're rotating around, we multiply that. Should we?
So if you hit, yeah, right, well, that's not hard, right? So we can check to see. One thing we can certainly check is to check what A times 1, 1, 0 is. That's not going to be quite sufficient to verify that this is the right thing, but it will definitely tell us if we're wrong. We should get 1, 1, 0 here, right? And indeed we do. Yeah, we do. So, I mean, this is basically what we're doing is we're adding these two guys. So we just get 1 here, and then since we have the negative, we get 0. So we do get that, which means it is preserving the axis. Another thing you could do is you could take the determinant of this and make sure it's 1. That would show you that you got a rotation. Well, actually, that would give you the, no, it's not quite enough. You could also take A transpose and, well, so this almost is its own transpose, not quite. But I mean, we know these are normal because we normalize them all. So the columns are all unit vectors. And you can kind of see right away that these are orthogonal. Like these two columns. You got a 1 and a -1, right? And same with these two columns. You can check to see that these are orthogonal, I guess. 1/4 plus 1/4 is 1/2, and then this times this is also 1/2. So it's a negative. So this is an orthogonal matrix. It's an orthogonal matrix and it sends this to one side, and it's, well, you'd have to check the determinant as 1. But I think that almost is enough. They want to check where Z is. It's not enough. I mean, that would tell you this is a rotation, counterclockwise rotation about this axis, but then checking where Z goes. Fun times, right? Now, okay, so just the other thing for B, you said that you knew how this works. Much easier. This is a much easier problem. Why is it much easier for all of you at home?
If you move your upward axis the direction of the 1, 1, 1 vector, then it's just a circle around each axis. And it ends up being 1, 1, 0. I did this in my E&M class.
1, 1, 0.
Or it's the 1 vector. Sorry, it's like 0, 0, 1, 1, 0, 0, 0, 1, 0. I think. Check.
You move like the
You
first
flip the
base is just the
axis.
second.
Very good. Okay,
Yeah,
so
you
that
flip the axis.
this is actually, we have language for this, guys. Remember our language for this. This particular rotation, as you guys are mentioning, I think you all know what's going on. So I can't, it's kind of hard for me. All right, actually, let me do this. Give me a second. So try to make these about the same. So let's say these are about the same length. Look about the same, almost. All right. Well then, okay, so I can. And this will help, I think, with visualization. So let's say we do this. This is supposed to be a unit cube, even if it doesn't look like. Okay, so we'll take the unit cube. There's our cube. And we're gonna, where's 111? 111 is right here. So we can take this line. Right. And then the point is what's going to happen if we rotate by 2 pi over 3 is everything is sort of symmetric about this line. You can imagine a cube, you can spin it along that line. And what will happen is precisely what you said, right? You know, this guy, well, like maybe you start with E1. E1 will go to E2. E2 will go to E3, and E3 will go to E1. Right? And the thing about that, so that using what we were saying earlier, that tells us, I think, what you were just verbalizing, right? The way of writing down this matrix. This matrix is called a weight matrix. Elementary, close. Doesn't swap to. Right. What do we call those that swap a bunch that are not elementary? This is actually a matrix you get from the permutation 1, 2, 3, the cycle permutation. Good stuff. Permutation matrices are all orthogonal matrices. All right, guys. Well, that was fun. I feel reinvigorated. I'm going to go make some chicken corn chowder for my kids. Enjoy it.
Thank you.
Thanks.